Charles' law. And this is a direct law. This says that volume is directly proportional to temperature. And so again, we have to keep the other properties, pressure and moles, are constant for this to be observed. First, I'm going to have a cylinder, and it's going to have a movable piston such that the pressure inside, P in, is equal to the P out. So if the outside pressure becomes greater, then the piston will go down. If the inside pressure becomes greater, then the pressure will go up. So the pressure is always equal. And then I have some particles in here, like yaw. So they're at some given temperature, and then I'm going to have a Bunsen burner. So the Bunsen burner is heating up the particles. So what's going to happen when I heat up the particles?
Particles move faster?
Yeah, the particles are going to move faster. So if the particles are moving faster, they're going to create more pressure, and they're going to move the cylinder out until the pressure inside is equal to the pressure outside. These particles are moving much faster. Faster particles increase volume until pressure equals. This is a direct relationship. So what we can see is that if I look at volume versus temperature, as I increase the temperature, I increase the volume. This is a linear relationship. There's also a really important caveat for this one. And for this one, you must use Kelvin. Why would you think we might have to use Kelvin?
It's so we don't have negative temperatures?
That's exactly right. So volume is directly proportional to temperature. If I had a negative temperature, because you have to have a positive volume, can I have -3 liters of gas? Does that make any sense at all? I don't understand how. I don't think there's a way to imagine negative volume. So basically, remember Kelvin is take Celsius and add a number to it so that it never goes zero. So Kelvin has an absolute zero. If volume is directly proportional to temperature, I can turn this into an equality. Volume is equal to a constant times temperature. Now let's solve for K. What's K equal to? In this case, it's different. How do I isolate K? What would I have to do?
By temperature?
Yes. Divide by temperature. I have a very good helper today. I'm going to divide both sides by temperature. And on this side, temperature cancels with temperature. And I get that the constant is equal to volume divided by temperature. So in this case, because it's a direct relationship, if I double volume, then I will also double the temperature. Does that make sense? And so if I double both the volume and the temperature, then this quotient here will stay the same. Yeah? If I have 2V divided by 2T, I still get V divided by T, right? So basically you get V1 over T1 is equal to V2 over T2. And so we could have a problem for this one. If a gas with a volume of 2.80 liters shrinks to, so if the volume 2.8 liters shrinks to 2.57 liters when the temperature is 0 degrees Celsius, what was the initial temperature? Question mark. Okay, so similar idea. I want to identify my variables. What's V1? What's T1? What's V2? What's T2? So V1 is 2.80 liters. T1 is, I don't know. That's my goal. What was the initial temperature? V2 is 2.57 liters, and T2 is 0 degrees Celsius. Okay, so this might be the first thing is, first idea is identify variables. The second step would be convert. Do I have to convert any variables here?
The temperature?
The temperature. So 0 degrees Celsius plus 273.15 equals 273.15 Kelvin. So that's this one here, 273.15 Kelvin. I can't have Celsius. If I want to, I can convert them to Celsius after I'm done. But when I'm doing the equation, I need to have Kelvin. And then let's find the relation. So it's V1 over T1. I made this one harder, I think. V1 over T1 is equal to V2 over T2. And I want to find T1. What's T1 equal to? Aha. How do I isolate T1? Well, one thing I would do is I would get it out of the denominator. I do not like it in the denominator. T1 cancels with T1. And then I will have T1 on this side, but I want to get the other stuff out of the way. I'm going to times by T2 over V2. And over here, I'm going to need T2 over V2. All right, so then I cancel. I'm going to cancel T2 with T2 and V2 with T. And then I get, okay, so what's left? That looks like a mess, doesn't it? But I get T1 is equal to V1 over V2 times T2. And so then I'm going to solve. So that's going to be equal to V1, which was 2.80 liters. 2.80 liters divided by 2.57. Do we do that right? Yeah, so the volume went down. We're finding the initial temperature. So the initial temperature is going to be higher. That's correct. So then that's times 273.15 Kelvin. So it got the temperature got cold and the volume went down, but the earlier temperature must have been higher. I think we also have 3 sig figs that we're stuck with here. And so T1 is then 297.595, and it's accurate to 3 sig figs. And this is Kelvin.